Hi, I'm Kristan Bromley, 2008 World Champion, World Cup Series Champion and European Champion in the sport of skeleton bobsleigh. Yeah, weight is absolutely critical for our sport. Weight means more energy means faster sliding, so the more weight you have, the faster you will go. The athlete's weight is important, but it's the combined weight of the athlete and sled that's more important. So for example, we're allowed to change the weight of the sled between 33 and 43 kilograms, which means that a lighter athlete can choose a heavier sled and a heavier athlete has to choose a lighter sled. The reason we do that as a sport is it tries to equal the total weight as a package. Ideally, if we were just considering weight on its own, then the heavier the better, but there's always a compromise to that, and the compromise is the shape of the athlete and thus the aerodynamic drag. The athlete's shape and position is absolutely critical to the performance, and the reason why is well, there's two reasons. One is the shape influences the aerodynamic drag, and therefore the resistance to the sled and the athlete going down the track. But secondly, the athlete's position on the sled totally dictates the control that the sled has on the ice. So the balance of the sled on the ice is very important, dictated by the athlete's position on the sled. The sled has two runners, and those runners are shaped with a curvature. Now, with the centre of gravity of the athlete, if it's right in the middle of that curvature, then the sled is balanced in the middle of that rocking horse, if you like. If the athlete is too far forward, the sled tips forward. If the athlete is too far back, the sled moves back. Now, the implications of that is at the back of the runner there are grooves, and you want to have those grooves biting the ice to give control. So if the athlete is too far forward on the sled, there'll be no control because there'll be no grooves contacting the ice. Lift is important when considering aerodynamics. However, when you're in a curve with 5 times the force of gravity, the G-force effect totally dominates, and the lift, which is relatively small in comparison, really has a small marginal effect, but it's something we don't really consider. We can steer a bobskeleton. It's a very subtle steer. We don't have a steering wheel and we don't have runners that twist and turn. However, what we use is the difference in friction between one side of the sled and the other side to create a frictional moment that actually creates a steer within the track. There's two mechanisms for steering, and that's one is shifting the body weight, and by shifting the body weight we can put more emphasis on one runner than the other, or we can actually twist the sled. The sled is designed to be torsionally flexible, so by pushing with this shoulder and an opposite knee we can twist the sled, and what that does is it changes the contact of each runner with the ice, and therefore we can create a differential between each side of the sled. Yeah, we use both the head and feet to steer at times. Imagine putting your hand outside of the car window on a motorway at say 90 miles an hour. You can feel the forces pulling. It's the same when we're travelling down a track. If we shift our head to the left or to the right, it acts as a rudder. Again, in a curve it doesn't work because the G-forces dominate, but on a straight section of a track, the head acting as a rudder is actually quite an effective steering mechanism. We also use our feet. We only use our feet when we need an extreme steer, because when we put our toes down there's obviously friction. With friction it slows us down, so we don't really want to do that too often, but when we need to change direction quickly to avoid crashing, then the toe is a very effective steering mechanism. We use the head to two things. One is the rudder effect for the aerodynamics, but secondly, by moving the head to the right, we in effect shift our body weight to the right. And again, what happens there is a change in the way that the runners interact with the ice, which persuades the sled to go to the right as well. So looking to a particular direction is a good way of creating a very subtle steer. Yeah, the athlete's clothes and equipment is one of the fundamental parts of the sport's performance. The suit we wear, the helmet we wear, the gloves, the running spikes, the clothing, it's absolutely key because it's obviously a performance item. With a suit, there's two there's two balancing factors. One is the aerodynamics, and just like in swimming with the shark skin textured suits, it is the same with a skeleton suit. We're travelling very fast through a fluid, and the roughness and texture of that suit has a part to play. However, if you make that suit too stiff, we can't run in it. So at the top of the track, we have to have flexibility in the suit. So we're always again battling with this compromise of flexibility for running and stiffness and roughness and texture for, if you like, increased aerodynamics. There probably is an optimal fabric out there. We probably haven't found it yet. We're continually pushing the boundaries in this area. Adidas, UK Sport, they're all challenging the kind of conventional thinking. But is there an optimal material? Potentially. Have we found it? Perhaps not. The start is another key area of performance. We have two forms of energy to drive that sled down the track. One is the push start, which is kinetic energy, and the second is potential energy, which is the height. So it's very important to accelerate as fast as we can using our legs as an energy source. Accelerate that sled, jump on board, and then we let the gravity take over. So the push start is absolutely key. Our whole off-season programme from March until October is purely dedicated to explosive power development. So weights, sprint training, core exercises, just generally getting stronger and faster. But the difference between sprinting upright on a track and pushing a skeleton is that we're bent over. So the position that we run in is very different to a normal sprint position, so we have to train for that as well. The start gives you an initial advantage, so the faster you start, the bigger advantage that you have. The start is only a small part of the run. Once you're then on the sled, it is the driving skill that then will dictate whether you win a race. Yeah, a slow start can be compensated by better driving, but there is a limit to what that start is. So, you know, if you're half a second behind on the push, then absolutely not. But if you're only 1/10 or 1500ths behind the fastest push, then yeah, you can pull that back through brilliant driving. Yeah, well, at the start, obviously, we need to have a mix of control in the lateral direction, but free running in the forward direction. Otherwise, the sled will just totally go out of control and hit walls. We've got to have some kind of control. So what exists at the top of the track are two grooves, and those grooves are the same width apart as the runners, and the grooves allow the runners to sit in them and run freely in the forward direction, but offer some kind of lateral resistance. That means when we push a sled, we can put all our force down, knowing that the sled's going to go forward and not sideways. The grooves run for approximately 30 to 50 metres, and that depends on the track. So within that 30 to 50 metres, we've got to sprint, dive on, get into our particular position on the sled, at which point the sled goes onto the flat ice after the groove ends, and then you're totally with no stability. The corners of the track need to be banked simply to hold you in the track. With all tracks we have between 15 and 20 curves, and each curve has a slightly different radius. Now with the radius and with speed comes g-force or g-acceleration, and as you come into a curve, that g-force pushes you up, and if the curve wasn't banked, you'd just continue to go up and fly up the track like you would say in a roundabout on a playground. So as we come in, the track has to then bring us back down again, so the curve essentially to control that g-force. Each curve has a slightly different shape to it, and a different geometry, or a different bank, if you like. And each shape, therefore, induces a different g-force, and that g-force is felt by the athlete. So as an athlete driving into that curve, when the g-force comes on, I feel that pressure within the body, and I use that pressure as a steering trigger to dictate how I come out of that curve at the exit. So the way that the curve is banked differently means that I have to steer each curve differently down the track. Yeah, we can't steer the sled by just by watching where we're going, because if you imagine a horseshoe-shaped curve or a 360-degree loop, when you enter the curve, you can't see the exit, you can't see 10 metres in front of you. So the way we steer a sled in a curve is by feeling the g-force and feeling the pressure, rather than watching where we're going. It's absolutely key that we do feel those pressures. sport skeleton will reach up to 90 miles an hour on the fastest track in the world. The track in Whistler, the 2010 Olympic Games, was a very steep start and was a very steep section through the first few curves. So we were already up to 40-50 miles an hour by curve 2, curve 3. Whereas, say, on traditional tracks in Europe, it takes about half a way down the track to get up to 50-60 miles an hour. So it depends purely on the track itself. Yeah, the ergonomics of the sled are a key part of its design. It essentially allows the athlete to fit into it like a hand in a glove. We have a close fit with the saddle around the body. Our handles are specifically fitted to the sled in a certain way to make sure we have maximum control and grip and maintain form. So the ergonomics dictate aerodynamics, they dictate control, and they dictate everything we do on that sled, so it's absolutely key. The incline obviously affects the speed, and speed will also affect G-force in the curves. It's more the G-force that we're designing a sled for rather than the incline itself. So the incline is a part of the equation, but it's mainly the G-force that's a defining characteristic. Friction is a huge source of energy loss. It accounts for about a third of the energy lost down a run. So the mathematics behind the sport have found out that a third of the energy from top to bottom is lost due to friction. If we can change friction by even a small percent, 1-2%, it can have a defining effect on the performance, and it can make a difference between winning a medal or not. The aerodynamics is another area of energy loss, and again the mathematics suggest that it is again a third of the energy lost down a track. So friction and aerodynamic energy is about equal according to the mathematics of the physics of the sport. Yeah, so when we talk about friction in the sport, the friction, sliding friction between runner and ice is one energy loss, whereas the aerodynamic drag, even though it is a form of friction, we term it as aerodynamic drag, and that's resisted force to motion due to the aerodynamic effects. Yes, a skeleton is designed so that we can make structural changes. We can change the shape of the runner, we can change the stiffness torsionally, we can change the way that we steer, so the sensitivity of the sled. And they're three key areas that the athletes tune into to try and adapt that sled to their own style. Before a race, we get 3 training days, and during those 3 training days, it's a combination of coach, mechanic and athlete coming up with a combination of settings that's going to be right for the race, and those settings will include consideration of weather, the track itself, the way the athlete's feeling, condition of ice, and a lot of other factors. So there's 3 days of preparation, but when it comes to the race, it's only the athlete that can make the adjustments. The coach is not allowed into the parc fermé area. So on the race day, it's the athletes that's making the changes. And the athlete can only make the changes to the runners. That's the only thing they can change on the race day itself. So when we play around with the Allen keys and we have an Allen key bolt, essentially what we're doing is we're putting pressure at the back of the runner, and that's creating a rock, a curvature into the runner. Right. So the more we screw that Allen key in, the more that runner curves.
Pushing a flexible ruler together.
Absolutely.
Sort of,
Absolutely. So by pushing that ruler in more, it creates more of a rocking horse effect. Right. And essentially what that means is the sled will be more unstable on the ice, but ultimately it'll have less friction. The athlete's always playing, and our sport is always about a balance, about compromise. You're always playing with a balance of control and stability versus energy loss. So the more control you have, the more friction exists because the blades are cutting the ice. They're giving you grip, but they're also losing energy. So the athlete's always playing with a level of stability to right on the point where they can just control the stability of the sled and therefore minimise the frictional losses incurred down a track. So that's when the skill of the athlete takes over. A skilled athlete can control a sled that's very unstable, whereas a new athlete, a learning athlete, will obviously require a more stable sled. We're always playing with extreme lines. I think the nature of an athlete is to push boundaries on all levels, whether it's the technology, physical development, etc., etc. When it comes to driving the track, that's no different. By taking a higher line, potentially could mean that you'll get a faster exit out of a curve. You might be able to use some of the energy in the curve to create acceleration. And we're always playing with those lines, and we can steer the sled. So we can steer up to the roof, or we can keep it low and resist the tendency of wanting to push the sled up. So we have a choice. Right. Not always the high line is the fastest, but we have to find out, again, the mix of physics versus what we can actually achieve as a skill level as an athlete, and what we're willing to do in terms of risks. Because obviously, a few inches off a roof at 80 miles an hour is quite a dangerous move.
And do the athletes...
Myself, as an engineer and an athlete, I like to break the whole track down from physics, maths, and put that thinking into the way I drive. Whereas there are other athletes out there, like for example, Shelley Rudman, who would essentially just get on it and drive based on the technical support and work that her team does for her. She's just a natural instinctive driver. So totally different ends of the scale, and both very successful. The rules of the sport dictate what we can build a sled from. So the frame inside the sled has to be steel, the runners have to be a stainless steel that we have to buy from a factory in Switzerland. The pod around the sled frame can be a plastic, it can be metal, it can be carbon fibre, any kind of composite pod. The saddle itself has to be steel. So even though we're governed by these categories, there are still hundreds, if not thousands, of different types of steels and composites. So we can still change the characteristics of the behaviour of that sled by choosing different categories of those materials. Yeah, carbon fibre is it's an extremely important material in all sports. It's light, it's strong, it's very stiff. Now obviously we talked about weight, and weight isn't really the issue that we're focused on with skeleton, but its stiffness is. So at 90 miles an hour we need that shape to hold its form. So the forces, the downforce, the lift, the torsional kind of effects of the wind can pull that pod out of shape. So we need it to be very stiff, and that's why we choose carbon fibre. Yeah, carbon fibre is a great material because you can build the structural properties how you want. So by laying the fibres in a certain direction, we can make it stiffer or less stiff. Now with a sled, we need stiffness in certain directions, but we also need flexibility in others. So we need it to be able to twist so that we can push our shoulders and knees and create this steering, but we also need it to be strong in normal G-force in the curves. So we designed the carbon fibre so that it is strong along the sled, but it is torsionally quite flexible so that we can steer it. The profile of the runner is essentially what gives us the grip between the sled and the ice. The sharper the profile, the more grip. The more grip, obviously you don't hit walls, but with grip comes friction, and with friction, energy loss, and therefore slower. So by making a sharper runner, we get more control, but we lose time. By making a less sharp runner, we, if you like, we make a more efficient runner, but we have the potential to hit the walls, with potential to go out of control. So it's a balance again between just on the limit of control for the athlete to maximise his performance. No, the way the groove is cut, if you imagine a round bar, which is what we have to use, we have two round grooves that are cut into the top of that bar. Now those grooves can be closer together and wider apart. So we still have part of the runner surface that has got a round shape to it, but the grooves that are cut into the runner create an edge, and it's that edge that creates a bite into the ice. If we had a purely sharp knife digging into the ice, there would be too much grip. So we have to create a flat area on the bottom of the spine, as we call it, the knife edge, so it doesn't penetrate too much. So we do want it to sit on the top of the ice, not cut into it. On the rear of the runner, from the centre point to the back, we have two grooves. And the grooves are designed so that when they're machined, they leave a spine, and by having those two round grooves wider apart, we can create a wider spine that's left in the middle. If we machine the grooves closer together, we get a thinner spine. Now a thinner spine obviously creates more grip, but bleeds time through extra friction. A wider knife sits on top of the ice and doesn't bite in, therefore it doesn't have as much friction but is very unstable. So we spend a lot of time getting the right width of knife and the actual geometry of that edge. It's quite sharp, it will cut the nail, but it won't cut my finger if I press on it. The runner itself is subject to a lot of forces as we're travelling at 90 miles an hour and 5G, and for such a thin bar it does have a tendency to bend. So what we're designing into the sled is a structural support that supports the runner around the centre point, that stops the runner bending too far and therefore yielding and plastically deforming. Now those structural elements, even though they support the runner, they obviously protrude out the bottom of the aerodynamically styled pan. So we've had to work with wind tunnels and CFD, computational fluid dynamics software, to style and shape that part so that it works with the pan in an aerodynamically efficient way, as opposed to just a structural element that creates drag. Our sport is all about energy, and the maths and the physics allows us to understand where that energy is lost, how we can become more efficient with the performance. So fundamentally, by understanding the sport through maths and physics, we can understand how to become faster, and it's that maths and the physics studies that allows the engineers to make the changes to make the athletes win medals.
Excellent.
Without the machine, the athlete could not compete in the world's top 20. But once you're in the world's top 20 and the world's top 10, the athlete then takes over, and that comes down to a combination of mental strength, focus, determination, skill, commitment. Can they do it on the day? Can they do it when there's 20 million people watching at the Olympic Games? That then becomes a completely different pressure cooker environment, and the athlete wins at the end of the day.
Kristan Bromley, thank you very much indeed.
Welcome. So this is a skeleton sled. It consists of a variety of different components. One of the key components are the runners, which is a stainless steel round bar that's bent at the back, bent at the front, and is bolted to a steel frame that sits inside the sled. And the steel frame inside the sled is designed to take the loads. It's designed to create the steering and the sensitivity of the steering and the connection with the athlete. Around the frame we have the composite pod. Now the composite pod is designed to work with the athlete to maximise the aerodynamics. So it's got a shape to it, it's curved, it's convex. We can't design concavity into the sled, it has to be convex by the rules of the sport. But that can be made of any material from plastic through to metal, but we choose composites because we can tailor the structural characteristics. So we've got the runners, we've got the pod, we've got an internal steel frame that is the main load-bearing structure. We have little guides here that offer a little bit of lateral stability to the runners. So you can imagine at 5G at 90 miles an hour with 100 kilos weight on the sled, that these runners get pulled around a lot with the forces. So these guides are designed to create some kind of strength and stability to the runner so it doesn't bend. On the back side of the runner, on the sled, we have the saddle. And this saddle, this is a simple one, but we do have complicated designs. But this saddle is designed so that the athlete lies in it and it grips the stomach and the chest area. The handles allow the hands to be by the side. We're not fastened into the sled and we're not fastened onto the sled. It literally is just there as a locator. So the position and the shape of that is very important to where the athlete sits on the sled. And then simply on the top we choose a neoprene padding. It's just at the moment it's just taped to the pan because the international body, the jury, needs to cut into that sled on a daily basis to inspect and make sure that the sled complies with the rules. So we have to have something very accessible. So we just choose a very, very simple neoprene padding on top, which offers a degree of comfort for the athlete. So that's the sled. Team Bromley is about helping world-class athletes to win medals by developing the world's best cutting-edge technology and equipment. And we do that by harnessing the, if you like, cutting-edge skills of some of the world's best companies in materials, in aerodynamics, in design, in carbon fibre, metals, etc., etc., and coupling that with our focused design skills in making and designing, developing sports products. And the whole purpose of this is to help athletes to win medals. Team Bromley has multiple disciplines and engineering capabilities. We do everything from design through to rapid manufacturing, using new rapid manufacturing technologies, through to composites, materials, through to advanced machining, through to aerodynamic simulation. So the engineering skills within our team are like a mini Formula One team, essentially. It's everything that's needed to make a performance product win Olympic or world medals. And that has to be everything from the way it looks, through to the way it behaves, and the way that it performs, and also meet regulations within the international governing bodies. So it's a real multidisciplinary approach to the engineering side. There are, I suppose, design engineering, there are CAD engineers, material specialists, we have product designers, aerodynamic engineers. But rather than have individual engineers for specific categories, our approach is to be integrated and bring all those together. So the engineers that we have multidisciplinary experience. So they might be a CAD operator, they might also be a product designer, they might have experience in composites, and they can bring those three together, and then by coupling into that the aerodynamic discipline as well, what we get is very rounded individuals that can think about the whole ethos of designing performance products by considering how everything joins together. The real world is everything affects everything else. Individual disciplines don't sit in their own right and isolated. We have to bring them all together, and that's really the true essence of what Team Bromley is about. A passion for sport helps, because if you're genuinely passionately involved in something, then the sources of innovation and enthusiasm for that innovation delivery becomes more effective. But I think fundamentally you have to have a passion for engineering and technology fundamentally, because that's essentially what drives it. But by coupling your passion with that, then we can really push innovation to a new level.